Okay, so we have looked about revolving one function about the x-axis, the y-axis, a different horizontal line, a different vertical line. We looked at an example of each of those. So what happens if you decide, you know what, I am actually going to revolve two functions about an axis. So let's call this f, let's call this g, we'll just make them pretty simple. Say we revolve this region about the x-axis. So if that's the case, then g gets reflected down here when we're drawing it, and f gets reflected down here when we're drawing it. And because we're revolving this region, this is all blank space. So there's like a tunnel in the middle of this space, in the middle of this strange thing, and then there's an outer thing. So we get this whole solid, but in the middle, it's actually blank space. Well, we actually know how to find this volume, and we know how to find this volume. So if you want to find the volume of the whole thing, you actually just do one minus the other. Okay, so this one is getting subtracted, and this one is getting added. So we're taking the solid volume if g weren't there. We're taking the solid volume if it were just g, and then subtracting the g from the f. So thinking about this, we're now dealing with a washer, right? Like you would put on a bolt or a donut, whatever you want to call it. And so our cross-sectional area is now pi times big radius squared minus pi times little radius squared, where this is r and that's r. And then of course, remember, we have a little width to this thing, right? And so that's our dx. And so the volume of this washer is that, or simplified to pi times big R squared minus little r squared dx. So that's what we're really looking to do when we're finding the volume with two things rotated around. We need to find our big radius, our small radius, and then subtract them. But it's really coming from this idea of finding the volume of one, finding the volume of another, and subtracting them. So in this case, we know that our big radius would be f, and our little radius would be g, and so this would be the integral from a to b of, we'll put the pi out front, f of x all squared minus g of x all squared all times dx. So that would be your formula where both of these functions are rotated about the x-axis. Now if they're not rotated about the x-axis, well, that's where you need to bring in the same concepts that we talked about before. Do you have a line y equals k? Then maybe your radius, your small radius, is g minus k, and your big radius is f minus k. Or is k up here? Then maybe your small radius is k minus f, and your big radius is k minus g. Or maybe you have functions that are rotated about the y-axis, and you've got a g of y and an h of y. Or maybe they're rotated about the line x equals negative something, and then maybe it's g minus 2 minus a negative 2, and h minus a negative 2 are your radii. Or maybe it's over here, and you need to do the axis minus this function, and the axis minus this function. So there are lots of different possibilities, but the same thing always applies. You're looking for the big radius, and the smaller radius, and then you want to subtract your volume of the big girl and your volume of the little girl, right? So that's sort of what we're looking to do. So let's look at an example of a problem. It says, let R be the region in the first quadrant bounded by the graphs of y equals square root x and y equals x over 3. We're looking in the first quadrant. So the first thing we need to do is basically sketch these functions. Square root x, let's see here, 1, 2, 3, 4, 1, 2, done, bum, bum, it looks like that. X over 3, well, it has 0, 0. And then you go over 3 up 1, and then over 1, 2, 3, and up 1, then over 1, 2, 3, and up 1, and this should intersect right there. So it looks like that, right, where this is square root x, and this is x over 3, right? This is supposed to be a linear function right here, and this is our root x, and they should intersect where square root x equals x over 3, or where 3 root x equals x, or where 9x equals x squared, which is x equals 0, or x equals 3. So that's how we know that they meet there. x equals 3, x equals 9, whoops, x equals 9, or x equals 0. Those are their intersection points. Okay, so we found the region, and now we want to know, find the volume of the solid generated when r is rotated about the vertical line x equals 1. Okay. Wait, x equals 1 or x equals negative 1? X equals negative 1. So x equals negative 1 is right here. So there's x equals negative 1. We're going to revolve this thing around that axis. And so it comes all the way over like so, right? And it creates this weird thing. It's got a big gap in the middle here, right? Holy moly, this thing is weird. It's got this weird gap here in the middle, and then it's got sort of this weird thing like this. So it's pretty hard to visualize, I would say, right? Because over here, you're going to get this giant circle like so, and it's going to be this very strange looking, like, I don't know, somebody has a good idea for what that should be. Regardless, when we're looking at one of these washers, it should look like this, and we need to be thinking about our little radius and our big radius. Now, the first thing we want to notice is this little width of the washer, we're moving up and down, so this is a dy, which means we need to be integrating everything in terms of y. So that means we need these functions in terms of y. So if this is square root x, then x needs to equal y squared, positive y squared because we're on the positive side. And if y equals x plus 3, then this is x equals 3y. So our function that is farther on the right is 3y, right? Because this is farther on the right than that, and this is farther on the right than that, and this is farther on the right than that, and this is farther on the right than this, right? So farther on the right is 3y, and farther to the left is y squared. So let's think about these radii now. Our smaller radius is right there. It's that distance right there. So that distance is y squared. And that distance is 1. So my radius should be y squared plus 1. But again, that's y squared minus a negative 1. So my little radius r, that's y squared minus a negative 1, or y squared plus 1. My big radius is here to here. That's my big radius. R, which is 3y, that's 3y plus 1, or 3y minus a negative 1, so that's 3y plus 1. So that's my big radius and my small radius. And once you found that, I mean, it is just literally a piece of cake, because all I need to do is basically fill in this formula. So I know I need the pi. I'm going to integrate over my y values. That's from 0 to 3. My big radius squared, that should be 3y plus 1 squared. So that right there would give me the volume if I just revolved 3y around the line x equals negative 1. But I didn't. I revolved two things, so I need to subtract off my smaller radius squared, and then all of that's going to be multiplied by the little width of the washer, which is dy. So now I would have to multiply that out and integrate it, but I've got the formula for my volume. And again, this is pi times the integral from c to d of my big radius squared minus my little radius squared, all dy. So that's giving me the big volume minus the little volume should give me the volume of that thing. So in the interest of looking at, say, another example, what if we revolve this around the line y equals 3 instead? So revolving this around the line y equals 3. Again, here's my square root. Here's my linear function. They meet right here at the point 9, 3. So say I revolved it around the line y equals 3. So now this is getting revolved up around, and it should look like this, like this. So it's going to create some sort of an interesting disk that looks like that. So still creating a washer. But now, fortunately, the width here is a dx, so everything should be in terms of x. So again, we need to find our little radius and our big radius, and then we're pretty much set to go from there. So here's our little radius right there, and our big radius is from here down to here. Okay, so big radius is the line 3 minus that function value, right? That's the function value. That's 3, so if I subtract the function value, I get that distance. So we already know that, and so that's my big R, and it should be K, which is this. That's 3 minus my lower function, which was x over 3. That's my big radius. And my little radius right here, same thing, except for I'm subtracting off a bigger function value. So that should be 3 minus the square root of x. That's my little r. Okay, so putting that all together, I want to integrate from 0, x equals 0, to x equals 9. I should have the integral from 0 to 9 pi times my big radius squared, 3 minus x over 3 all squared, minus my little radius squared, 3 minus square root x all squared, and that is all times 3x. So that's about as bad. I don't know, I guess these problems can get a little bit worse if you have to find like a weird intersection point, but that pretty much takes care of some of these nasty volumes of revolutions when you've got two functions that are being revolved around a strange axis. So that should take care of it.